revolving electron, or we can also say magnetic dipole moment due to a revolving electron, and that is what we are going to discuss. In this discussion we are going to derive 2-3 important results and which are most probable for your exams, and not only for exams but also it improves our understanding. So kindly just go through the entire discussion. The first point, magnetic moment or magnetic dipole moment. So initially we had derived, if you have a current carrying circular coil at a point along the axis at a distance x, we derived, and we compared this with magnetic field due to a bar magnet. We compared these two magnetic field, to arrive at magnetic moment is actually the product of current and area. So the magnetic moment can also be represented by the Greek alphabet mu and current into area. So the unit of magnetic moment is through this definition or expression, current unit being a area meter square. So the unit of magnetic moment is ampere meter square. At the same time, we know that energy of a dipole in a uniform magnetic field, we derived it to be minus m dot b, or we can say minus mb cos theta. This is the energy of a dipole in a magnetic field. So the unit of energy being joule, and so we are only going to consider the units. Leave the negative sign, and you don't know the magnetic moment m unit, and magnetic field unit is Tesla, and cos theta being trigonometric ratio, thus ratio of the two sides, the units cancel, no unit. So this does not have unit, and dropping negative sign, you know that unit of magnetic moment is joule per Tesla. So the unit of magnetic moment is either ampere meter square or joule per Tesla. So you consider a nucleus, an electron is revolving around the nucleus in a circular orbit. Okay, so first we have to find out, because it is a charge going in circles, so when a charge is moving, current is flowing. Because electron is moving in circle, because of the motion of electron, tiny electric current is produced. So we will first have to find out that electric current, and then you have to multiply that with this area. Suppose the radius of this circular orbit is r. So the magnetic moment due to the revolving electron is the current due to this motion of electron around the nucleus multiplied by this area pi r square. So first let us derive the current, and after that we are going to sort of compare this with, or we will be trying to bring in the angular momentum notion introduced by Bohr. Because this is an electron moving around a nucleus, obviously you have to consider the atomic theory. So what is it? Let us also try to understand before that. Suppose if an electron is moving in a circular orbit, this is the radius and the velocity is along the tangent always. The angle between these two is 90 degree. Angle between the radius and the velocity, or you can say that the perpendicular distance to velocity is radius. And if an electron is moving with velocity v, its momentum is mv. So classically angular momentum is r cross p. That means momentum multiplied by perpendicular distance. This is written as modulus r modulus p sin theta n cap. So if you consider only the magnitudes, r here is r, p is the product of mass and velocity, here theta is 90 degree, so sine 90 degree. So we will get the angular momentum as mvr, mass, velocity of the electron and radius of the orbit. So the Bohr said the angular momentum in the nth orbit, the first or second or third, where n being the principal quantum number, is the product of h by 2 pi. So in the nth orbit, here the electron is in the nth orbit. We are not sure. This is not neither the first orbit nor the last orbit. So electron is in a particular orbit. Let us say the quantum number of that orbit is n. So angular momentum in this orbit, let us say nh by 2 pi. This is one sort of thing. And the next thing, current due to moving electron. This is an important relation. So the current due to moving electron. Suppose the electron is going in circle. Here is where, here you stand and you look at. So for the electron to, let us assume the time taken for the electron to complete one circular orbit, let us say t. So you consider point A or point B or point C or anywhere, the electron in one time period crosses only once. Hence, the current we usually write as charge by time. So if you take time as time period, this charge, the electronic charge is E, crosses a point only once in one time period. So the current due to an electron equal to charge by time period. So then this can also be written as, in one way, charge into 1 by time period is frequency. So if you multiply charge into frequency of revolution of the electron around the nucleus, then that also constitute current. But I'm going to take up this relation only. So the current is equal to charge by time. See here what? Time taken for one complete revolution is time period. If the radiuses are in one time period, it goes around only once. So the distance covered will be equal to circumference 2 pi r. We know that speed of the electron is v. Speed is equal to distance by time. When the time is equal to time period, that means in one time period, it goes around only once. Hence the distance covered is equal to circumference 2 pi r. Using this relation, time period is equal to 2 pi r divided by v. That I am substituting here. Time period is equal to 2 pi r divided by v. Hence, current due to an electron around the nucleus is EV divided by 2 pi r. Hence, we have arrived at two important results here. One is current due to an electron moving in a circular orbit is the product of electronic charge and frequency. This nu is frequency of the electron around the nucleus. Or it is E by 2 pi into speed of the electron divided by radius r. So this is the current. So once we have found the current, substitute the value of current here in this equation. Let us find the magnetic moment. Magnetic moment is equal to EV by 2 pi r, EV by 2 pi r into pi r square. Cancelling pi r and square. So the magnetic moment is equal to EVR divided by 2. So here, in order to just look at this angular momentum expression, it is mvr. So we have got vr, so m is missing, so I'm just multiplying and dividing by m. So e by 2m, I'm writing it separately, e by 2m into mvr. So mvr. So mvr being angular momentum, because angular momentum mvr, according to Bohr's theory, angular momentum is nh by 2 pi, hence mvr can be written as nh by 2 pi. And before that, let me write angular momentum. So mu is equal to E by 2m into L, where L is the angular momentum of the electron, mu is the magnetic moment of the electron. So just take up this point, mu by L. So mu by L equal to E by 2m. So here this point is magnetic moment per unit angular momentum is a constant. Magnetic moment per unit angular momentum is a constant. Magnetic moment per unit angular momentum for an electron is constant. So you can just and its unit, charge by mass. It is half of the charge to mass ratio. Charge to mass ratio is actually 1.73 into 10 power 11 something it will come. So it is half of it. So it will be like 6 point something into 10 power 10 coulomb per kilogram. Its unit is coulomb per kilogram. So just find out charge per mass ratio. It is roughly around 0.6 into 10 power 11 or 6 into 10 power 6.5 into 10 power 10 coulomb per kilogram. You try to remember this value, and then we further add magnetic moment is equal to E by 2m into this thing. So what is it? E by 2m into L we are adding. So when you add L, in place of L you substitute NH by 2 pi, E by 2m into NH by 2 pi. So let us try to kind of this all of these things. Separate mu equal to, and I'm sending a n, so EH by 4 pi m, EH by 4 pi m. Also this can be written as mu is equal to n times, usually h by 2 pi can be called as h cross, so EH cross by 2m, n times EH cross by 2m. So the magnetic moment due to a revolving electron can be written as n times EH by 2 pi 4 pi m, or it is EH cross by 2m. So then here the value of all of this, mu equal to, what about the magnetic moment of the electron in the first orbit of hydrogen atom? So n is equal to 1. When first orbit means n is equal to 1. In such case, the magnetic moment is equal to EH by 4 pi m, and that value is equal to 9.27 into 10 power minus 24. You can write it as ampere meter square or joule per Tesla as we discussed. So the magnetic moment of the electron in the first Bohr orbit is this thing, 9.27, and this thing, and this happens to be the minimum possible magnetic moment. You see n, the n's values will be not 0, 1, 2, 3, etc. And the minimum possible value of n is 1. For the minimum possible value of n, the magnetic moment of the electron, this magnetic moment is due to going around in circles, so it is orbital magnetic moment. So orbital magnetic moments value, the minimum possible value is EH by 4 pi m, that is equal to 9.25 into 10 power minus 24, either ampere meter square as a unit or joule per Tesla as a unit. This value is called Bohr's magneton. So if this value is Bohr's magneton, let me call it MB. We call it Bohr's magneton MB. So in general, magnetic moment is equal to n times MB. We call it n times MB or Bohr's magneton. So the possible magnetic moments values are n can be 1, 2, 3 or etc. So the magnetic moment due to orbital motion of an electron can be mb or 2mb or 3mb, etc. So since the magnetic moment cannot take all values but the integral multiple of Bohr's magneton, so the magnetic moment is said to have quantized. Like charges, like electric charges, magnetic moment of a revolving electron is also a quantized quantity.